Good morning. Thank you for coming. My name is Olivier Bégassat. I'm with PegaSys R&D. I will be presenting today an expose on our aggregation protocol Handel and the most recent part of that saga, which is the newly obtained convergence results relating to Handel. So this is the structure of the expose. In a first time, we'll be going over what Handel is, what it does, why we need a protocol such as Handel. I will also shortly or quickly be discussing some of our test results, which we obtained with real-life tests over AWS. And the second half of the talk will be dedicated to the last claim in the title, this convergence claim, which is basically how we modeled Handel as a random graph, and the results we obtained in terms of completion time and so on. Okay, so let me get started with, first of all, what is Handel? Handel is joint work with Roger Collard, Nicolas Gailly, Nicolas Liochon, and myself. Handel is a large-scale Byzantine fault-tolerant aggregation protocol. It exists right now as a paper on the archive. There will be an updated version of that paper by the end of the month. Handel is also implemented as a Go library, which is open source and which you can find on the consensus GitHub, and which is what we used to do large-scale tests. Okay, so as I said, Handel is a large-scale aggregation protocol, and you might be wondering what got us interested in the problem of aggregation. Aggregation actually is a natural problem that appears when you look into proof-of-stake blockchains in particular. You may think, for instance, of the problem of collecting attestations in Ethereum 2.0. In our estimate, we realized that most of the aggregation methods that are out there are defective in some way, which makes it not really suitable for the decentralized context of Ethereum 2.0 or blockchain in general. They all share at least one defect of the following. Either they are slow, which means that they don't really scale well in the number of nodes. They might be wasteful in terms of bandwidth consumption. Centralized methods, for instance, are extremely fragile, and even decentralized methods, such as binary tree-based solutions, are vulnerable to Byzantine attacks. When you have a hierarchy between nodes, the nodes that rank higher in that hierarchy have more power and thus have more power to eclipse the contributions of other nodes. So the fact that there is no really satisfying large-scale Byzantine fault-tolerant and very efficient aggregation protocol has a few undesirable consequences. If you think of blockchains, proof-of-stake blockchains that employ committees to do the validation of blocks, let's say, or the notarization of blocks, this imposes severe restrictions on committee size, on feasible committee sizes. Other blockchains, such as Ethereum 2, which also use randomly sampled validator committees, but which require the whole validator set in the end to confirm a block by means of basically a whole epoch passing by, they also suffer from this defect. In this case, it manifests in block finalization time, which is on the order of a few minutes, of a few epochs, rather than mere seconds. So there's good reasons to try to improve upon the existing schemes. And Handel is our solution to this problem. Handel aims to solve the issues I just raised. And as a network protocol, it achieves the following. It is very fast, a very fast form of network aggregation. It is actually provably polylogarithmic time and polylogarithmic in message complexity. Here, logarithmic and polylogarithmic is always with respect to the total number of nodes. It is it is very efficient in that it burns very little in terms of machine resources, and the network load is also very small. It is also compatible with various sorts of network configurations. Let me put it this way. It works very well, and in spite of vastly heterogeneous latencies, as well as vastly different machine capabilities. And it is Byzantine resistant. So Handel, I guess the main takeaway is that Handel is very fast and scales and is resistant to attack. Okay, so I'll present very quickly the results we obtained. So as I said, Handel was implemented as a Go library. And we used this implementation to test Handel on AWS, where we ran BLS signature aggregation over 4,000 participating nodes. These nodes were always 2 nodes apiece per AWS instance. And the instances were located in all the AWS regions, 10 different AWS regions, in order to ensure varying latencies. And I guess what Handel achieves is that it is able to aggregate those 4,000 signatures in under a second, and with an average per node communication complexity, which is on the very low end. Here is a graph that pits Handel against the complete graph aggregation technique. So the reason we chose the complete graph as a reference, let's say it this way, is because in the case where the number of dead nodes in a Handel run is extremely large, Handel actually degenerates to a complete graph scenario. So you can see that the time complexity to aggregate those 4,000 signatures with a 99% threshold is nearly constant, quite independent, almost independent of the number of participating nodes. In this slide, you can also see that the progression of network consumption is very tame compared to the complete graph, which is O of n squared. And finally, what happens in the case of many fail silent nodes, so nodes in the network that just don't participate. If you want to, for instance, aggregate 51% of all the available signatures of the total number of potential nodes, let me say it this way, Handel still works extremely well in spite of the handicap that nearly half of the network is down. Okay, so this was a short presentation of what Handel is, what it solves, and what it is capable of in terms of performance. I will now dive into one particular aspect of Handel, which is the way it structures communication. And I do this in order to motivate the random graph model that I will talk about later. So the way communication is structured in Handel is, has taken a lot of inspiration from a technique called binomial swap forest, which was described in the San Fermin paper in 2008 by Justin Capos et al. And in this network, which will be the Handel network, the nodes are known in advance. They have an identifier. They may have a signing key and a way to reach them, which might be an IP address or a Tor address. And quite importantly, actually, for the analysis, the nodes are initially randomly shuffled. Communication is structured in levels, which will become clearer as I show a few pictures. And nodes all do the same job of aggregating. So all the nodes do the aggregation job in parallel of one another. Furthermore, aggregation happens on parallel in all levels simultaneously or concurrently. So to try to make this a little more concrete, let me describe to you the way communication works. So imagine you have 8 nodes and you're node 5. In the first level of communication, you will be talking to, as it were, your immediate neighbor. And in the second level of communication, you'll be talking to the 2 next, or neighbors once removed, basically. And next level, you'll be talking to 4. And the number of people you potentially talk to always grows like a power of 2. So to make this a little more transparent, you can imagine that there is a binary tree in the background, and that the people you talk to at level k are those nodes whom you can reach. Well, if you want to reach them, you have to move at least k levels up that binary tree. And to make this even more manageable, you can even segment communication and have draw a diagram where the nodes are duplicated, just on the diagram, of course. And level k communication always links nodes on level k minus 1 to level k. So if you take all of these graphs together, you get a very nice, very large graph, which is a directed graph, because communication is always one way in Handel. And this is the graph of all potential communications. In this graph, everyone can actually talk to everyone else, but of course Handel tries to minimize the actual amount of communication that's happening. So I'll give you an example now in pictures of a typical run in Handel, again with very few nodes. Again, this is the graph now with the edges not being highlighted as sharply as they were earlier. This is the graph of all potential communication, and Handel only wants to explore a tiny fraction of that. So Handel is supposed to work with nodes that start at different points in time. So you may imagine that node 1 in this scenario is early to the party and starts sending its contributions to its level 1 peers, and then the other nodes start joining in. 2, 4, and 7. Node 1, in the meantime, has already moved to the next level. This continues. Node 1 at this point is communicating on 2 levels simultaneously. So this is this business about concurrently communicating on all levels. And you may have noticed that, well, this happens actually here. You may have noticed that nodes 5 and 7, which were previously active, at some point seem to be inactive. So I'm taking a sort of bird's eye view of this, and this is only here, this business of being seemingly inactive is only here to highlight the fact that communication has latency, and so node 5 may be seen as not reaching anyone at any point in time, even though this is only due to latency. And this continues, and at some point you might encounter a special situation where node 3 in this scenario has managed to aggregate a complete aggregate signature of its current level binary tree, basically. Everything below it at that level. And this triggers a special event called a fast path, where it decides to send its complete signature up to that level to many people simultaneously. But of course, this doesn't happen in isolation, and at the same time, there's other people talking. Okay, and finally, you may have noticed in this scenario, node 6 never participated, and okay. Okay, so with these pictures in mind, I think we can now motivate our modelization of Handel as a random graph. So the random graph will be the graph we introduced earlier. You can imagine that you have all of these nodes structured in levels, and any one of these arrows can fire up with a probability that only depends on the level at which the arrow is. Furthermore, you have potentially dead nodes, so there is also a random variable that decides which nodes are alive and which are dead. And this is a static version of the dynamic version of Handel we described earlier. So again, I will give you a short example. So there is no passage of time. So when you draw the edges, they are basically drawn once and for all. And you also have dead nodes that you selected according to this liveness random variable. And once you have the dead nodes, well, you can as well erase their contributions. They are not going to participate in the network aggregation protocol. And then the question becomes, well, given such a configuration, what is the best signature that a node can aggregate? And if you look level by level, for instance, if you look at the very top, there's a question marks because it is, as of yet, undecided how many contributions were aggregated. If you look level by level, you can deduce the number of contributions that were maximally obtained by a given node. For instance, if you look at the 6, which is sandwiched between the 2 dead nodes, it inherited the 3 from the previous level, and it was also contacted by node 0, which contained 3 contributions. And since all of this is completely disjoint, you can aggregate willy-nilly. There is no problem. Okay, so the main question now is basically the numbers on the top row. How do they behave? What we would like to do is, what we would like to have as a result is that most of the nodes that were live managed to aggregate everything there was to aggregate, or nearly everything. And we would also like this to be a rather stable result, which means that not just that there are nodes that aggregate almost everything, but that actually most nodes aggregate everything. And this is the result we obtained very recently. So the main takeaway, before I expose the theorem to some extent, is that with arbitrarily large probability, which you may fix initially, this will be a parameter of Handel, Handel converges in polylogarithmic time for most live nodes. And I will try to make this slightly more precise. So I just put this there because you have to set some notation a bit, but I'm not really going to be worrying too much about this. You have a maximal proportion of dead nodes in the system, you have a threshold you want to reach, and you have a failure probability, which you're willing to accept. And with these things set, the theorem states that basically if you've set these parameters at the beginning, then upon communicating with roughly n cubed nodes on each level, where n is the height of the graph, so it's the log of the total number of people, with basically communicating at each level with n cubed people, the vast majority, or proportion tending to 1 of all live nodes, will aggregate nearly everything there is to aggregate in the system. So this is a slight downgrade from the theorem we had initially proved just 2 weeks ago, until we realized it failed, where the constant 3 was replaced by 1. And this theorem is now just a conjecture, and it states that you don't really need to communicate with n cubed people. You should actually just be able to communicate with n people on every level. So it would be really not just polylogarithmic, but actually logarithmic. Okay, so this conjecture, just to give you an idea, is actually borne out by simulations. Those are simulations which we ran in our simulator called Wittgenstein. For various proportions of fail-silent nodes or dead nodes. And you can see the bottom axis, the x-axis is logarithmic scale. So you can see that the slopes, the lines you get, the graphs are basically straight lines, which is supporting evidence for our conjecture that it should be logarithmic time. And this remains true even if you have some mild Byzantine behavior. However, if you have the strongest form of Byzantine behavior, which we've identified, it degenerates to quadratic time, at least log squared. Okay, so let me give you a brief overview of how we obtain the result. The analysis happens in 2 stages. The first stage is a homogenization phase. And then there is a second phase called controlled reproduction, basically. Homogenization is basically answers the question: how large how large are the batches you need, basically? The complete subtrees in the lower levels. How large do you have to take them in order to be assured that the mix of Byzantine nodes and live nodes, honest nodes, is pretty much homogeneous? And beyond that, the problem almost takes care of itself. So, as I said, the first stage is about creating homogeneous batches of nodes. And this is where it is really important that we have a random shuffling at the beginning. If you take control of the randomness in Handel, then you potentially encounter severe problems. Okay, so the main tool we use for this is a set of inequalities that are very classical in probability theory. They are called concentration inequalities. And what they tell you is how likely a random variable is to steer away from its mean. So in this case, the mean is NP, and you wonder how likely is a relatively large deviation from that mean. This is the relatively large is the delta in this stuff. And using these kinds of inequalities, you can establish that in order to have really homogeneous batches, so batches where you expect to have roughly the correct proportion of Byzantine nodes, you only need to talk at a very small number of levels. You basically need to talk at log of the number of people of levels. And and this is strong enough that you have actually very good probabilistic insurance or reason to believe that all of the batches you create are actually homogeneous. Once you've done this homogenization property, which requires only basically big O of n communications, you get into the reproduction phase. And here the idea is also very simple. You start basically with a batch, with plenty of batches of nodes where complete communication has occurred. So all the honest nodes have assembled the complete aggregate signature of their batch. Of course, excluding potentially dead nodes or Byzantine nodes who may send wrong information. And what you want to do is to see how likely is it that two batches reproduce to the next level. And here, reproduce means that you are going to take two batches of a given size, and you want to have a batch that has, again, aggregate signatures that are obtained by gluing together these aggregate signatures, which is of size nearly double. So here's a picture to try to illustrate this. The yellow batches at the bottom are fixed size set of nodes that were able to aggregate everything almost. And they, of course, communicate with one another, but also with other people. I didn't draw those arrows. But you only really focus on the communication within the yellow batches. And you wonder how likely is it that someone who was yellow initially just doesn't get contacted by another yellow node from the neighboring batch. And you want to do this in such a way that the proportion that survives is at least 1 minus some small quantity epsilon. And if you do this on many levels, n levels, you had better require that epsilon be very small, of the order of some constant divided by n, in order to leverage the fact that 1 minus epsilon to the power n will converge to nearly to 1. Okay, and then you put everything, all of this stuff together, and you just look at the event, something goes wrong. So this is a very pessimistic way of doing aggregation. There are, of course, ways to aggregate where something goes wrong, but nonetheless, most people still aggregate almost everything. But we look at the very stringent requirement that everything goes perfectly well, and thus at the contrary case where something goes wrong. And using those concentration inequalities yet again, we are able, with some mild analysis, to show that if the number of people we contact per level is roughly n cubed, then the probability, well, this upper bound is actually something that tends to 0, which establishes that nearly everyone aggregates nearly everything in Handel. Thank you very much.